This lesson is on free fall. We're going to talk about the definition of free fall and how the acceleration in this case is simply due to the force of gravity. And so whenever we come into a free fall situation, that's a value that we're always going to know, but it's not necessarily given to us. Okay. Then we're going to talk about what happens to the velocity of the object as it goes up, and at the top of the arc, what happens to it. Then we'll look at problems and how the kinematic variables are going to be impacted by free fall. So first off, free fall is a situation where the object is not in contact with any other object. It's not in your hand, it's not on a string, it's not coming out of a gun. Okay, the only force that's going to be acting on the object is gravity. So examples of this is I drop a ball, or I jump straight up, or I fire an arrow straight upwards. Okay, so what happens is that this problem becomes nothing more than a one-dimensional kinematics problem. If we shoot it at an angle, it becomes a two-dimensional kinematics problem, and at that point we refer to it as a projectile situation, but really the two are related. Okay. Also, when we look at free fall, it's important that we always ignore air resistance. If we include air resistance, the problem gets a little more complicated, and the math needed to analyze it becomes more complicated. So we keep it at a fairly simple level here. So we talk about the acceleration due to gravity. Anytime you're close to the surface of the Earth pretty much looks flat. The curvature is so gentle that it's hard to notice it. And so gravity pulls all objects down towards the center of the Earth, or we like to just call it downwards. And this acceleration is measured to be about 9.8 meters per second squared downwards. If I write it in vector format, I end up with 0 meters per second squared in the x direction, or I hat, plus negative 9.8 meters per second squared j hat. A lot of times, because we just wanted to get do mental math or get an estimate of the value, we frequently use g as simply 10 meters per second squared downwards. The 10 allows us to do a lot of things math-wise very easily by just moving decimal points or multiplying by 10. So it's also important to note that I give you g in full vector format. Don't automatically assume it's positive or negative. Okay, before you do that, in your problem, you need to choose a positive direction, and therefore the opposite direction would be negative. So if g is in the positive direction, g becomes positive. If g is in the negative direction, g is negative. Okay, so in the example given above of negative 9.8 meters per second squared, in this case I had defined g, or defined the positive direction, to be the standard coordinate system, or up is positive, down therefore is negative. So there's a difference between objects that are dropped versus objects that are tossed. Okay, an object that is dropped has an initial velocity of 0 meters per second. Okay, I simply hold it, I let it go, it starts to fall. Okay, so in this case my acceleration doesn't change, it's still going to be downwards at 9.8 meters per second squared. Okay, if I have an object and I throw it upwards, okay, it will have a non-zero initial velocity. Okay, so although my velocity will be upwards, my acceleration will be downwards. So they will have opposite signs. Okay. Frequently, the best choice for positive direction is the direction of your initial velocity. So if I throw an object upwards, then that up would be the positive, my velocity, initial velocity would be positive, and acceleration would be negative. Okay, and I'm only interested in the period when the object is in the air. Okay, I don't care about what happens while I am tossing it. Not important. After I catch it, not important. Only when it's in the air. So let's get a little practice with acceleration. Okay, remember, acceleration is the change in velocity, or the rate of change in velocity. Okay, so if I use acceleration, or g, as 10 meters per second squared, and I drop a ball, okay, what velocity does it have after 1 second? 1.5 seconds. 4 seconds. Okay, these are three different numbers, and the use of g as 10 makes the math very easy because I can multiply 10 times almost anything very easily. So after 1 second, okay, well, I started at 0, 1 second later, I'm going to be at 10 meters per second. Whoops. Sorry. After 1 second, I will be at 10 meters per second. After 1.5 seconds, okay, I'll be at 15 meters per second. After 4 seconds, 40 meters per second. Okay, and that's why we frequently use 10, because the math becomes really easy. For another example, okay, if I throw a ball upwards at 20 meters per second, so it's going up at 20, how much time is needed for the ball to temporarily stop? Well, if my acceleration is 10 downwards, I'm subtracting from my velocity. Okay, so after 1 second, I started at 20, 1 second later, I'm at 10, 2 seconds later, I'm at 0. Okay, so right there, I've temporarily come to a stop. I don't stay stopped because gravity continues to act, never stops. Okay, and I start to accelerate downwards and speed up now. Okay. So let's talk a little bit about the top of that arc. Okay, as Isaac Newton says, what goes up must come down. Okay, so right at the top of the arc, okay, my velocity does become 0, but it doesn't stay there. Okay, acceleration stays all the time. Okay, all the time it's going to come back down at 9.8 meters per second squared. Okay, frequently a lot of people think, well, I get to the top and I don't have any gravity at the top. I don't have any acceleration at the top. I think people confuse the terms velocity and acceleration. They're related, okay, but they can be completely different numbers. Okay, so acceleration is the change in your velocity. If I have no acceleration at the top and I have no velocity at the top, that means my velocity never changes. It stays floating in midair, and we know things don't float in midair unless it happens to be a balloon. Okay, so at some point, yes, my velocity reaches 0. That's the maximum height or top of the arc, and a nanosecond later, it starts to come back downwards because my velocity now starts to go negative or downwards. So let's look at the various kinematic variables. Okay, an object in free fall will always have a vertical acceleration of 9.8 meters per second squared downwards. Okay, you may need to split the problem into two sections, kind of an up section and a down section. The reason you split it up is because you have that extra piece of information right here at the top. Okay, as the object goes up, it slows down, slows down, slows down until it gets to that final velocity of 0, or temporarily it becomes 0 right at the top of the arc. On the way down, now I know what my initial velocity is because I start my initial velocity at 0 meters per second. This is kind of the same situation as if I dropped it from that height. Okay, and again, if necessary, draw a picture. Okay, another way to look at the velocity is in the velocity graph. Okay, so if I throw an object straight up, it has a positive velocity to begin with, right there. Okay, and acceleration means I will have a slope of negative 9.8 meters per second squared. Okay, at some point I reach the top of my arc, okay, where my velocity is 0, but I don't stay 0. It doesn't flatten out or anything. It continues past 0. Now my velocity is negative, okay, or I'm basically falling, okay, and at some point I will catch it and the ball, my analysis finishes at that point. Okay, so let's look at a sample problem. Okay, this is sample problem number 1. I want you to try and do sample number 2 on your own, and we'll talk about that one in class. Okay, so in sample problem number 1, I have this guy Andy. He drops a coin down a deep well and here's a splash some 3.62 seconds after he drops the coin. And the question is, how deep is the well? Okay, try and do it on your own. Pause the video here and see if you can do it on your own. Okay, Hopefully you were able to solve this problem on your own. It's not that complicated. Let's look at the variables that we have, okay? He drops it, so this is a free fall problem, so I have acceleration of 9.8 meters per second squared. I haven't assigned a sign to it yet, okay? And actually, I'm going to assign a positive sign to that because I'm going to define positive to be down because that's the initial velocity of the coin. It drops, so downwards it makes the initial velocity. And here's my well. Okay. And 3.62 seconds later, I hear a splash. So time-wise, I know 3.62 seconds. And because it was dropped, I know what my initial velocity is, 0 meters per second. If I'm looking for distance, okay, since I'm looking for distance, I would use this formula. Okay, distance is equal to VIT plus 1/2 GT squared. Okay, so here's the G. I should really call it A, okay, but it's the 9.8 that I used. Okay, well, VI is 0, so I can ignore that part. And distance then just becomes 1/2 of 9.8, or 10, and T becomes 3.62 squared, and that then becomes 4.9 times 13.1044, and if I plug that into the calculator, I will get a value of 1 second, 4.9 and 13.1044, 64.2 something, 64.2, but I'm going to take it to 3 sig fig, so it's just 64.2 meters. That's a deep well. Okay, 64.2 meters is very deep. Okay. So here's sample problem number 2. A ball is tossed straight up at a speed of 12 meters per second and caught at the same height that it started at. Calculate the maximum height of the ball and calculate the total time that the ball is in the air. Try and do this on your own, and we'll talk about this in class next time. Thank you.